So what we've seen is, okay, how do we describe coordinate frames with respect to reference frames, how we move things around with transformations, which is basically either rotations or translations, how we combine them so that we produce more complex transformations, and now we'll see some different expressions of basically orientation, and we'll finish with some ideas of how to switch frames and so on. So what we can show is that the transition between two arbitrarily oriented coordinate frames translated can always be expressed using these basic transformation frames that we heard. No matter where are two frames relative to each other, we can always calculate the transformation that takes us from frame A to frame B using elementary translations and elementary rotations if we combine them the right way, right? Now, when talking just about orientations, we can show that this can be achieved. So if we have two frames arbitrarily oriented relative to each other, we can calculate the transition from one frame to the other with up to 3 elementary rotations, right? So we can always find 3 elementary rotations. If we put them one after the other, we can go from one frame to the other, right? This was chosen by this person. Do you know who this is? Euler. Nice. Was, not is, yes. Who basically proved that you can go from any orientation to any orientation using 3 subsequent rotations, right? It's what we typically call these days the Euler angles, which is not too specific, but it's pretty used in robotics. Why it's not too specific? Because they're basically different, how do you call this? Different orders of transformations that you can use in order to achieve the same result. So you can describe the orientation as a rotation around Z, rotation around X, rotation around Z, rotation around X, Y, Z, rotation around, X, Y, Y, X, Y, Z. They're different sequences. They're called sequences, right? So sequences used for these things. So when we say Euler angles, we typically mean 3 rotations around X, Y, and Z, and they are relative to each other, if I'm not mistaken. Whatever. It's better when you talk about Euler angles or this kind of 3 rotations to always specify the sequence you used, just to be super clear. So it was X, Y, Z, X, Y, Z, Z, Y, whatever it was. All right. It's pretty used in robotics, so that's why I'm mentioning it. You will play a bit with it in later laboratory when we talk about trajectories. An even more weird way of explaining orientations is using a thing called quaternions. Anybody ever heard about quaternions? See people nodding. What's your experience with quaternions? So it's basically, quaternions is a number system similar to complex numbers. It is basically expanding the complex numbers. Complex numbers being combination of real and imaginary numbers, right? So we have a complex number C, consisting of a real part and an imaginary part, or I don't know, if you like it like this maybe. So quaternions is basically the same thing, but with more imaginary parts. So here I shouldn't call this C anymore, I should call it Q. C plus K D, right? So I have a number which consists of a real part and 3 imaginary parts. Can you imagine that? It's too imaginary, right? The point is that these quaternions, they have been developed and they are used to express orientation relative, two frames oriented relative to each other. These indexes here, they're imaginary indexes, and you know from just the imaginary part I, we have this relationship, how much is I at the power of 2? Sorry? -1. All right. Because if it was 1, it wouldn't be anything special. I mean, it's just 1. But this is the special thing. And it's the same thing for all the other imaginary parts, plus some extra relationships which we represent using this matrix, right? Because we can multiply I, j, and k between them. So with this matrix, we see what do we get if we multiply I with j, for instance. So I times j equals k. Okay, j times k equals I think. j, k, I, right. K, I equals j. And then these things are not commutative either, right? If I have ji is not k, it's minus k, I think. Ji minus k, right? The way I remember them is similar to cross products. So if I have basically this ijk can be these three axes, x, y, and z, and ij is basically the cross product of x and y, which is z. Cross product of y, x is minus z, so minus k. Simple. Or you can think of them as a circle. That's another way. I, j, k. So when I do I times j, I get k. When I do j times k, I get I. When I do ki, I get j. And if I go the other way around, I get with minus stuff. You don't need to remember these things by heart. I'm just explaining them for reference. All right. And you see that on the diagonal, I have -1 up there. Yeah. Okay. So there is 1 times 1. I have 1. But I times I minus 1, it's basically these relationships. Okay, it's weird. I have a link here, so when you open the slides at home, if you want to check, there is like a very nice YouTube video from 3 Brown 1 Blue. Maybe you know about the guy. Is very good visualizations on math concepts, and the quaternions video is like very good as well. How do we use this for rotations? If I have a quaternion, basically it expresses a rotation around an arbitrary axis, the purple thing, a rotation by angle phi. So any transition from one frame to another, can be expressed with quaternions. So I have 2 frames, let's say, and I can always find a way to rotate this one into that one if I rotate around one axis. Okay, you see what I'm doing here. I'm faking it a bit maybe, but you can imagine that this holds true. So I can go from this orientation to this orientation by choosing an axis, and no, I'm not getting there. So something like this. Right. So this purple axis is the axis of rotation, and then phi is the how much I need to rotate to go from this to this. Okay. And the relationship is basically, so I have, where is my pointer? I have the projections of this axis. So it's another way to think of it is like the coordinates of the tip of this vector here. Okay. They are basically constructing these 4 numbers here, A, B, C, and D. So A will be basically the cosinus of the amount I'm rotating, twice the amount I'm rotating, right? So if I rotate, let's say, by 45 degrees, okay, if my phi is 45 degrees, A will be cosinus of 2 times 45 will be How much? 2 times 45? 90? Cosine of 90? $365? No. You're blocked. 0? No? Okay, I doubt myself because I see you. Am I saying something wrong? All right, so let's say if I have an axis I'm rotating by 45 degrees, then the real part, the A, will be 0, and then this will define here the 3 times. So sinus of 2 phi will be 1, right? And then here I will have the B, C, and D there from the projections of this axis. You don't have to do these things. I'm just explaining again for reference, like, okay, how can we interpret quaternions as rotations, right? So a quaternion can be thought of as a transformation matrix as we saw earlier that takes me from one frame to another, just the orientation part, right? And the meaning of these 4 numbers has a geometric meaning that we can understand like this. Yeah, we can also define the inverse quaternion. We didn't talk about the inverse yet, but yeah. Now, final concept that we'll talk about, and it's something that you'll practice also in the laboratory. In robotics, we have a lot of frames around, right? A lot of things moving, and for each one we need to use a frame to describe its position and orientation. And many times we know the coordinates of something in one frame and we need to transform it in another frame. Let's say I have this robot and it has, let's say we have a reference frame for our whole, I don't know, production, what the robot is doing, right? And we have a, let's say a sensor, for instance a camera, that reports the positions and orientations of an object, but it will do it in its own frame, like the camera, you know, it understands things in its own perspective, right? So it will tell us the position and orientation of an object in its own frame, but we'll need to somehow transform it in the reference frame of the robot so that the robot knows where it has to go and pick anything up. It's similar to saying, like, I don't know, you know where is the door and you have to explain me where is the door. You know it from your perspective, all right, but I need to know it in my perspective. Like, okay, so if I want to go to the door without looking at it. So this is the concept of switching frames, right? Okay, how do I transform information from one frame to the other? And we'll first talk about points. So let's say I have, as we started with points, I have the information about the position of a point, let's say point P, in reference frame 1. So this is what I call P1. Let me also try to use this. I have one already on the board. So let's say this is frame 1. Okay, and I have a point. Let's call it, I don't know, this point. All right, and it has some coordinates. Right, it would be the distances along this axis. Okay. And for whatever reason, I want to express the coordinates of this point, let's say here, of this in this coordinate frame here. Okay, so let's say this is frame, as I have it in the example, let's say this is frame 0. So I know the coordinates of frame P, of point P in frame 1, and I want to calculate the coordinates of point P in frame 0. So I know P1, I know, and I want to calculate P0. This I don't know. Right? How do I do this? Like in our case, I will need to know where you are relative to me in order to be able to infer where is the door, if I know your coordinates, right? So in this case, we will need to know what's the transformation, what's the relative position and orientation of these two frames, right? If I know this, then I can do the transformation as we see on the board, right? So what kind of transformation I need? I need to know what kind of rotations and orientations I need to apply in order to start from this frame, from 0, and go to frame 1. All right? So I need to calculate basically what we will call the transformation from 0 to 1, or as we saw earlier, another way to see this is the position and orientation of frame 1 with respect to frame 0. We saw that this is the same thing, right? We can use frames, we can use matrices to express a frame with respect to another, or we can use these matrices to express the transformation from one frame to another. So the rotations and translations I have to do to go from this frame to this frame. Okay? Good. If I know this transformation, in this case R01, I can do this multiplication. Sorry, I'm running out of space here. So I can calculate P0 as the multiplication of R01 and P1. Okay? So if I know the coordinates of a point in one frame, let's say frame 1, and I'm looking at the coordinates of the same point in another frame, let's say frame 0, all I need is the transformation that takes me from 0 to 1, or the matrix that describes the position of 1 with respect to 0. It's the same thing. Okay? Let's see how this works. What is the size of this matrix here? What did we say is the size of the transformation matrices? 4 times 4. All right. What is the size of this point here? We said that and we're talking 3 dimensions, all right? What is the size of, sorry? No, it's 1 point.
3 by 1.
3 by 1, we saw, right? Can I multiply these two together? No, right? Because it's a 4 by 4 with a 3 by 1. So what we do when we want to work with these homogeneous transformations that we said that we have this 4 by 4 is I convert this to a 4 by 1 by adding one element at the end. So I have P1 will be the 3 coordinates we saw earlier, Px, Py, Pz, and at the end I will always add a 1. It sounds like an engineering trick, but it's actually a mathematics trick, right? So it will always have this value 1 here. Oops, sorry. It shouldn't have done this, but all right. Okay, good. So if I do this multiplication, what will be the result? If I have a 4 by 4 multiplied with a 4 by 1, it will be a 4 by 1. So it will be another point with the same shape as this. Will it have again the same shape? Let's see. What did we say about this one, right? What structure it has? And let me erase the quaternions because we don't need them now. I'm going backwards. We said that we have this 3 by 3 orientation, this 3 by 1 position, and here we had 0, 0, 0, 1, right? So if I multiply it with a point Px, Py, Pz, 1, what will be the result? And I don't know what will be the result here, here, and here, but I know what will be the result here. What will I have here? how do I calculate this point? This element? It's basically this column, this row, multiplied with this column, right? So if I do this multiplication, I will always have 1. So if I have points with this 1 at the end, and I multiply it from the left with a homogeneous transformation matrix, which always have a 0, 0, 0, 1 at the last row, I will end up with the same form here, all right? I know what you're going to ask. Can I multiply from the right? Can I? No, because I cannot do a 4 by 1 times a 4 by 4, sorry. I cannot do this, right? Because it's 1 column and I have 4 rows here, so it's not possible. Should do an X here. All right. So, once again, if I know the point, the coordinates of a point in one frame, and I know the transformation from another frame to this frame, I can calculate the coordinates in this other frame by doing the multiplication of the transformation with the point. All right? Let's quickly put some numbers here. It's not going to be super accurate, but yeah. Let's say point 1 has, I don't know, coordinates 1 here and 3 here. So it has coordinates 1 on x, 3 on y, and 0 on z. So P1 is 1, 3, 0. All right? Let's try to see what is the transformation between these frames, the way I wrote them. R0 to 1. And it's R0 to 1, which means I start from 0 and I go to 1. Right? So I start from this one and I move to go to this one. Or another way to think about it is, what are the coordinates of these 3 vectors and the origin with respect to this frame? All right? So let's see, what are the coordinates of these 3 vectors with respect to that frame? So what coordinates does x have with respect to this vector, to this frame? Imagine they are on the same origin, just focus on the orientation now. So x0 is pointing up, x1 is pointing down, so what, sorry? Minus? Minus 1, 0, 0. Very good. Right? Because it's in the opposite direction as x, and it's in the same direction, so it will have 0 on this y and 0 on this z. Good. What's the coordinates of y, of this y, of y1 with on this frame? 0, minus 1, 0, again because they're pointing the other direction. And z's? Sorry? 0, 0, 1. All right, good. That's it. We could have calculated by saying, okay, this is a rotation around z by 180 degrees. Right? If you see the transformation matrix for rotation around z by 180 degrees, you will see it has this form, right? Because this is basically rotated by 180 degrees. All right, and let's put some numbers here for the position. Let's say this is, I don't know, 6, and this is, let's say, 2. So, what is the origin of frame 1 with respect to frame 0? What is the position of the origin of frame 1 with respect to frame 0? What's this distance? 2, 6, because it's positive is this way, right? 2, 6, and 0. What should be on the bottom line? 0, 0, 0, 1. All right. Let's delete more quaternions and go to the left. We are like Arabs. All right, so if I do this multiplication, I should calculate where is P0, where is point P with respect to 0. So it would be this one, P1. So it's basically minus 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, 1, 0, 2, 6, 0, 1 times 130. All right, so let's try to do this multiplication. I should get a 4 by 1. So let's see, if I do this, what do I get? What is a bit higher? Minus 1, 1, minus 1, plus 2, 1. Yes. So this one, it is minus 3 plus 6, 3. This times this, 0. This times this, 1. It's actually the same coordinates. Good point. And it makes sense, right? Because this thing is kind of in the middle between these two and they rotated by 180. But we see that this distance is also 1. If this is 1 and this is 2, then this will be 1. And then this distance is 3. The same reason. It would have worked no matter the orientation, right? If this was like this matrix would have been a bit different, so the result would have been different as well. Okay. I have an example here as well, different numbers, but I thought of building it together as well, not just seeing it there. Good. Now that's one use. Another use is that maybe here I don't have a point, but I have another frame. Let's say, I don't know, this frame. So this trick doesn't work only with points, it works also with frames. So let's say I have again frame 0, I have frame 1, and I have frame 2. And now, what do I know? Let's say I know the transformation. So now I don't have just a point. A point will be just the origin, right? But now I have a full frame, so I don't have just a point. I have a full transformation, so I know, let's say, the transformation from 0 to 1, okay, from this one to this one. And I know the transformation from 1 to 2, so from here to here. I should be able to calculate the transformation from 0 to 2, right? Same idea. It's not just about knowing where is the point, but also how it's oriented, right? 0 to 2, right? Oh no, sorry, this I know, and I don't know this. How do I calculate it? I know basically that it will be 0, 2. It will be from 0 to 1, and then from 1 to 2, right? If I know how to go from Cluj to Brasov, and from Brasov to Bucharest, I know how to go from Cluj to Bucharest, in a way, right? Sorry, didn't put the whole example here. Right, so we can use this chain rule as well to calculate a frame with respect to another frame. Like if I know a specific transformation, as I saw from 0 to 1, and I know another transformation from 0 to 2, I can calculate the combination of the two. Right? Let's see a bit of dimensions here. What dimension does this have? It's a transformation matrix, so it's a 4 by 4. This is also transformation matrix, so it's also a 4 by 4. So the end result will also be 4 by 4, another transformation matrix. All right. Yes. Once again, these ones represent both the transformation. So how do I go from 0 to 1 and from 1 to 2? And also it expresses what is the orientation of 1 with respect to 0, or what is the orientation of 2 with respect to 1, right? So if I want to go from 0 to 2, I can go from 0 to 1 and from 1 to 2. Or I can say that, okay, this R02 represents the orientation and position of this frame with respect to 0. Different ways of saying the same things. We're gonna come back to this idea of, I'm insisting on this because we will come back to this idea of, a transformation matrix is both the action and the result. You will see why I insist. Any questions? Yes. If you know P, so if you know P0, let's say, and P1, if you can figure out what's the transformation between them, that's what you're saying. That's a good question. Is it unique? Is it only one way? Let's say you have P1. You know point in 1. Right, so basically you know some coordinates of this point in one frame, right? And you know the coordinates in the other frame, if you can calculate the transformation between them. Probably yes. Is it unique? I guess so. If it's unique, you should be able to calculate it. I'll think about how, because the problem is that you cannot invert these things because they are row. So you cannot do, I don't know, something like this times P1 minus 1, because this is a column, right? To do the minus 1, you need to be a square matrix. So you cannot do this. So then how do you do it? I'll think about it. It's a good question. But I think it's a unique transformation. So then you should be able to find it.
Can it be unique if we don't have the orientation of the point?
Sorry?
Can it be a unique transform if we don't have the orientation of the point?
The transformation between the two frames, I guess it can be. Like, let's say in this example, right? If I know P1 is the position of this point with this frame. This frame can be anywhere, right? It can be here, it can be here, as long as it's rotating around the point, it has the same coordinates, right? But then this happens with the same for this frame, right? Because it also has specific coordinates for this. So these two frames can be wherever, okay, but they always rotate relative to each other, the way I'm imagining it. I'm not sure if it's correct, what I'm saying, but yeah. That's why I'm saying I'll think about it. Or I'll research more. Come back. Any other questions? Okay. Then that basically completes our, so this thing is equal to this thing. Right, I got behind with the slides. So this basically completes our first step to making great robots. We now understand transformations, that we need to do the kinematics that we'll start talking about next week, the forward kinematics. In the laboratory, as I say, you will play with the transformation matrices, mainly with this last part. You will know a transformation in one frame, you will have to calculate in another frame. Any comments on the first laboratory? But I'll ask you about it in the laboratory, so not to spend time now. Any other questions or remarks or something you want to talk about?